philosophical question. Given the numerous planets in our galaxy, what is the likelihood that ours is the only one to host such an abundance of life? Mr. Beatty will take us through a brief history of life on Earth, the investigations into the conditions.
Hey everyone, thank you for coming. That's perfect.
Yep.
That'll be great. Some of you are old enough to remember a comedian named Bill Dana who had a character, Jose Menez the astronaut. And Jose Menez was once asked whether he thought there would be life on Mars when he got there. And he said, well, maybe if you land on a Saturday night. Okay. But you know, so this is going to be a talk that I want you to keep a really open mind about. This is a quote from the Martian Chronicles. Now, by the way, this picture, let me back up. This picture is of the Earth taken from the surface of Mars by a spacecraft on the surface of Mars. Now, I've brightened Earth just a little bit to make sure it would show, but that's the Martian landscape. So let's have recalibration here. You wonder. So in the Martian Chronicles, one Martian says to the other, "Do you think there'll be people living on the third planet?" That would be Earth. The husband says, "Nope, it can't support life. There's way too much oxygen in the atmosphere." So that's this calibration. Okay, so we'll start by trying to understand what life is. And there are definitions. Basically, it includes matter that has the capacity for growth, reproduction, functional activity, and continual change preceding death. I guess death is part of life. Now, there's a common misconception that organic matter and organic compounds somehow get conflated with the notion of life. I mean, gasoline is an organic compound, and we don't really think of it as life. So these are some simple organics in our everyday lives. Methane is natural gas. It's what a lot of us burn. It's an organic compound. So when you hear people talking about, ooh, we've discovered an organic this or that, that doesn't mean that they've discovered life. There's a big step between one and the other. But what we do know is that, as best we know, water is essential for life. Water is, it's so ubiquitous in our lives, we really don't think about it that much, but it's a very special molecule in that it's very strongly polarized in the sense that the one oxygen and the two hydrogens that are attached to it aren't in a symmetric arrangement. And as a consequence, it facilitates reactions, chemical reactions, and biologic functions. Now, there's another polar molecule in our world that we're familiar with, and that's ammonia, NH3. And so you could conceive maybe of having life that used ammonia. And in fact, there are some really extreme bacteria that could work with ammonia, but they still need water. Water is more polar, and also, here's the problem. Let's say that you went to some hypothetical planet that had oceans of liquid ammonia. Well, when water freezes, it floats, right? And caps and prevents further freezing. When ammonia freezes, it sinks. So a lake of ammonia would eventually freeze all the way through, leaving the fish flopping on the surface, trying to find some liquid ammonia to breathe. Now, our life forms are based on carbon structure. And it is conceivable. Silicon is a very similar element to carbon, and some people have hypothesized that maybe there could be silicon-based life forms. But the problem is that silicon, which can have 4 bonds just like carbon does, is unstable in water and oxygen, and the polymers, like the chains of carbons, don't exist. Okay. So next question, does life require sunlight? These are all the questions that we need to answer before we can go looking elsewhere, right? So let's have a show of hands. How many of you think that life requires sunlight? Good. Well, all right. So let's see a show of hands. Who thinks that does require sunlight? Photosynthesis, not. Who thinks not? The nots have it over the haves, and that's true. There are lots of what we call extremophiles. I kind of showed you the answer there, didn't I? that don't require sunlight, don't do photosynthesis. They get their energy from other settings, and they can live in some really extreme locations, including high and low tension, and even under intense radiation. So I gave a couple of examples here. These are worms at the floor of the Gulf of Mexico that are occupying a exposure of something called methane hydrate. It's methane it's water ice that has encapsulated methane, the molecule methane, and created a solid. And these worms are feeding on bacteria that use the methane for food. They're called methanogenic bacteria. They don't need oxygen at all. Here's another example. Now, I just want you to imagine if I took your standard high school chemistry Pyrex beaker. Fortunately, the ones at Chelmsford High School look more like this than they do it like this. That was a joke. Because this one has been exposed to 1.7 million rads of gamma rays. And so many gamma rays has actually changed the character of the glass. That same dosage was given to this particular strain of bacteria, and it did just fine. So there are bacteria, there are life forms that can exist in just incredibly extreme conditions. 6 weeks ago, my wife and I were in Chile to see total solar eclipse. We visited this geyser field, one of the highest in the world. It's at 14,200 feet. The oxygen is pretty thin. And I took this video of a little fumarole. Let's see if it will work here. There we go. You notice all the colored stuff around the edge? Those are critters. Those are thermophilic bacteria that really like and thrive in extremely hot environments. The water bubbling up out of that is boiling. So that gives you a sense. Oh, and this wouldn't be complete if I didn't show you some tardigrades. Tardigrades are all the rage right now. They're called a couple of different things. Moss piglets is one of them. The other one is something. Water bears, right. And they're very tiny. They're about 0.5 millimeter long. But they can survive. They've been around this Earth for 600 million years, lots longer than we have. And they're all over the Earth. There are about 1,000 different varieties. They exist in all kinds of environment, including the vacuum and radiation of space. And just a couple of months ago, there was an Israeli spacecraft that took a bunch of these to the moon, and it crashed. And so who knows? There could be tardigrades running all over the lunar surface right now. Who knows? All right. So with that as sort of a backdrop, let's kind of set the stage for how life came to exist on the Earth. So the universe, after the universe began, here's an important point. When the universe formed, there wasn't much around except for hydrogen and helium. No iron, no silicon, no carbon. Those didn't exist yet. It took generations of stars to form, live out their lives, and die, often exploding, to create all the elements that exist in the periodic table. We're the beneficiaries of that because here we are, some 12 billion years later, and we have, iron in our blood and carbon in our pencils, and, it's great. And so, but this process of forming stars continues, and we can see that happening in space. Here are a couple of images of gas and dust clouds out in space that have collapsed, and they form a spinning disk, and from that spinning disk, stars and planets form. This is a close-up of some of these concentrations inside the Orion Nebula. And so this is what we kind of think our solar system looked like just as it was forming. A lot of the gas had come together in the middle to form the sun, and the sun eventually ignited and started giving off light and heat. Out in the boonies, where we are, the gas and dust was still pretty cold, warmer near the center, colder toward the outside, and we ended up with this great array of planets that we call our solar system. This is sort of in that process. This could be Earth. Accumulating matter as it went along. You notice that it's kind of white hot, and that was, the Earth was a very hot place early on. In fact, it wasn't a very nice place at all, as this little video clip shows. Now, this thing here is the moon, just after it formed. And you say, my gosh, it's huge. The moon formed very close to Earth, far, far closer than it is now. And it's only after billions of years that it has actually migrated farther away. And it continues to do that at about that far every year. So when the moon was formed, it was actually very, very close to Earth. Let's see how this goes here. Yeah, I had a timeshare in this place, and it didn't work out well for me. Earth was still mostly super hot. It's still partly molten. Bombardment was happening all the time. There was still a lot of debris left over from the formation of the planets. You cannot imagine life happening in a situation like this. So a little bit later on, things quieted down a little bit. There were still impacts happening. The moon moved a little bit farther away. Can you imagine what the tides must have been like early on? And in fact, still, once our oceans formed, the tides were huge. And so there came a point, roughly 3.8 billion years ago, when things had quieted down enough that life took hold on our Earth. And the important thing to know is Earth did not have the atmosphere today that it had back then. We're actually working on our third atmosphere. The first one was this hydrogen and helium left over from the nebula. That got stripped away pretty quickly. Then we had an atmosphere that was mostly carbon dioxide and nitrogen. We started off, we worry about carbon dioxide a lot. We started off with a lot of carbon dioxide. And fortunately for us, it dissolves in water, and it forms seashells. And when those clams die, they sink to the bottom, and they form beds of carbonate and limestone on the bottom of the seafloor. And thanks to plate tectonism, they get sucked into the mantle of the Earth and take that carbon dioxide out of circulation. Good thing for us. Good thing for us. So the first living organisms were about 3.8 years ago. The key was when organisms called cyanobacteria came on the scene. They were the first creatures capable of creating photosynthesis. But before then, a more important question was, where did the Earth get its water? Guess what? It probably didn't come with the packaging that ended up making our planet. It had to be imported. There are a lot of different theories. If you took, we think of the Earth as a really water-rich planet, but if you took all of the water in all the oceans and all the streams and you put it together in one big droplet, it would look like that. Not very much at all. Really, there's not a whole lot of water there that we could deliver that much water with one really good-sized asteroid. Here's a close-up. So there's three little dots here. This is all the water on Earth of all kinds. This is all the fresh water on Earth, including in underground reservoirs. And this is all the water in all the lakes and streams that are on the surface of the Earth. This should be a cautionary tale that we kind of need to take care of our water, right? But the point is that there's not all that much water. It gets spread really thin around our planet. And so it wouldn't take much to deliver that water from elsewhere, either through bombardments from comets or water-rich asteroids. Some of the asteroids have water. It's easy to think that it was from comets because comets are largely water. But there's a chemical mismatch. There's a kind of hydrogen variation called deuterium. And the ratio of this heavy hydrogen to normal hydrogen is very different in comets than it is in our water. We know just from that alone that most of Earth's water did not come from comets. It had to come from other sources. All right, so we've got water on the Earth. It's 3.8 billion years ago. For a long, long time, astronomers and paleontologists and people who worry about these things imagine that life began in these sort of languid tidal pools where it was warmed by the sun and it was peaceful and the organic matter gradually concentrated and then somebody sprinkled some fairy dust on it and life began. That is unlikely to be what happened because remember the animation of how bad the Earth was getting beat up? Well, the bombardments continued. One notion, which I'll just mention in passing, is the notion of panspermia, that life actually began elsewhere and was seeded. The Earth was seeded with life from elsewhere. It's not too far-fetched. These two guys came up with the idea in the 1970s. And the notion is on Mars, which is a smaller planet with a much lower escape velocity, if life began on Mars first, which would be possible because Mars got cool before Earth did, then if something hit Mars hard enough, it could literally send fragments out from these edges here where at escape velocity, where they didn't get too badly shocked, launch them out into space, and some of those could eventually end up on Earth. Now, being in space is no picnic because there's all kinds of radiation. If you're just there by yourself, a little molecule in space, cosmic rays and the sun's ultraviolet radiation would take care of you very quickly. But the bigger shielding you get, the bigger the rock, the more shielding you get from all of this. And here's a table. If you had a rock that's, say, 10 feet across, that's about this diameter, a microbe in the center of it could last for 3 million years despite all the radiation. And so if you can get a big enough rock off the surface of Mars and somehow get it to Earth and have it plunk down, you could, in theory, have biology travel from Mars to Earth. Well, that's a little far-fetched. We're not going to go any further with that. There's no evidence that that actually happened. It's just an idea. Back in the 1950s, the Miller-Urey experiment attempted to recreate conditions on the primitive Earth to see what might happen. So they took a mixture of primitive gases, hydrogen, methane, carbon dioxide, and water, and then they sent an electrical spark through them and progressively boiled it and cooled it over and over again to see what would happen. Well, 2 weeks later, after doing this, the water had turned brown, and 15% of the carbon had been converted to organic compounds, including things as complicated as amino acids. Are amino acids life? Who says yes? Good, you're paying attention. Amino acids are not life. They're very involved organic compounds, but they themselves are not life. Okay. And so this notion of providing energy and water and the right chemical mix is what I want you to go away with, right? You need water, you need energy, and you need the right chemistry. That doesn't necessarily happen on the surface, and if the surface is constantly getting bombarded, maybe that's not the optimal place. More and more, scientists are thinking that the best place for life to have formed is instead on the bottom of the ocean near what are called these deep sea smokers, where heated water rich in chemicals is gurgling up from the seafloor, and this shows you what one of those looks like. This is a deep sea smoker in the Atlantic, I believe, and water is coming up through. It's basically like the Tadio geysers I showed you, except on the seafloor, and you can see the stuff coming out. This is all rich in organic material, and so it is this kind of setting that we're now looking to as the most likely place where primitive life began on the Earth. I want you to remember this because we're going to come back to this notion of these deep sea smokers a little bit later. So here are your cyanobacteria, the first organisms on the Earth that could create, could photosynthesize, could take sunlight and chlorophyll and turn it into oxygen. And it was only at that point that the carbon dioxide started to go down and the oxygen started to go up in our atmosphere. And thank goodness for that, because we have a really hard time breathing carbon dioxide. The oldest evidence that we have for these cyanobacteria is in what are called stromatolites, which are about 3.5 billion years old. So we know, here's an interesting thing. We know that the heavy bombardment ended about 3.85 billion years ago. And the oldest we think life might have formed is about 3.8 billion years ago. That's only 50 million years after the end of all the catastrophic impacts. That's not very long in a 4.5 billion year time period. In fact, it's entirely conceivable that life got a foothold, say, in the Indian Ocean, and a big meteorite came down, smashed and killed it off, and then life formed somewhere else. There is no reason why life couldn't have started at different times or at different places on the Earth, right? That's just something to take home. So here's a sort of timeline for you. Earth is 4.5 billion years. The earliest life form is 3.5. We are way down here in the last 7 million years of this 4.5 billion year time frame. What's important about this diagram is that for the great majority of the time that life has existed on Earth, it was only one cell. Multiple cellular organisms and, plants and animals as we know them came very late in the game. So when people ask me, do I think there's life elsewhere, I would say, yeah, I'm pretty sure there is, because it seems relatively easy with these conditions that you might form microbial life, single-celled bacteria, viruses, whatever you want to call them. Taking the step from that to, the prokaryotes, the us, that's a much larger step and perhaps a much rarer activity. One last thing I want to show you before we launch out into the great beyond. It turns out that all of these organic molecules in our world have what's called a chirality. They are either left-handed or right-handed, just like people, right? So if I take these are two organic molecules, and they can have a kind of symmetric construction, and biologists call them right or left-handed. Guess what? In our world, the organic molecules created by biology are all left-handed. All left-handed. So if you find, say, we find amino acids in meteorites, some of them that land on the Earth. And guess what? They're both flavors, both chiralities. So that's telling us that's not something derived from life. This could be a real impressive and unique indicator of organic material derived from life. Okay, so let's head out and check things out. The place that everyone looks to for possible life is Mars. And Mars is a wonderful planet. It's a smaller planet, about half the size of the Earth. Some of you came to the Mars talk earlier, and yet Earth is 75% covered with water, so Mars has about as much dry land area as the Earth does, if you think about it that way. So there we are, and it has some features that make it pretty Earth-like. It has a day that's about 24 hours long. It's tilted over. It has seasons. It has polar caps. Here's it has a lot of similarities to Earth in ways that other planets don't. Back in the late 1800s, these two guys, Giovanni Schiaparelli and Percival Lowell, were fascinated with Mars because everybody thought that there must be life on Mars. So they were studying it at a time when Mars came particularly close to the Earth. And the result of that was drawing some maps of this is kind of like a Mercator map. The poles are at the top and bottom, and the equator runs through the center here. And they saw these bright and dark regions. They called the dark regions mare, which means ocean. It means sea, excuse me. And so they imagined that there was this network of oceans. In fact, Schiaparelli called these canali, which is the Italian word for channels. Now, no one would imagine that the English Channel was built by humans. But it got translated into English as canals. And everybody would imagine that the Erie Canal was built by humans. So this notion of life on Mars took really a strong hold. Lowell, who left Boston and moved to Flagstaff, Arizona, where he built an observatory specifically for studying Mars, was fascinated, obsessed with Mars and drawing it. And he drew these maps showing now they're not just kind of irregular waterways, but they're actual like an interstate system that he imagined took water from the polar caps of Mars as it melted and brought it to the parched equatorial regions to feed all the crops. Those Martians were pretty smart. This is a painting by a famous space artist that sort of shows how that might be. Well, by the turn of the 1900s to the early 20th century, right? About 100 years ago, the French Academy of Sciences offered a prize of 100,000 francs for the first person who could establish contact with an alien civilization. This was in the time of Tesla and the beginnings of electrical engineering. There is a thing, though, except for Mars. They figured that it was too easy to establish communication with Mars because everyone knew that Mars was inhabited. Well, spacecraft that we eventually sent to Mars didn't actually show us all that much through telescopes. So when we finally went there with spacecraft in the 1960s, it was pretty disappointing. It was very lunar-like, with lots and lots of craters, and none of the geology that would suggest anything like what we had on Earth. Later on in the 1971, we sent an orbiter around Mars that basically mapped the whole planet. We found out lots of interesting stuff, including this feature here, which when blown up, looked remarkably like a human face, and there was this whole conspiracy, the face on Mars. When this originally came out, the scientists said, haha, look at that, it's a little mountain shaped like a human face, and people latched onto that like this was the real deal. Somehow those Martians, with somehow more powerful telescopes than ours, had zoomed in on us to find out what our facial features looked like, and then carved a mountain in our own, to let us know that we were there somehow. Well, turns out the face on Mars is really just a beat-up geologic feature. This is showing the same sort of lighting angle from a later spacecraft, and it's a nothing. But people still cling to the idea that face on Mars is real. We won't go to there. But what we did find out is that Mars wasn't just simply cratered. It had lots of interesting geology on it, including these ancient dried riverbeds, whole networks of them. There's one. This is a color-coded altimetry map that shows highs and lows. There was a lot of water flowing on the early history of Mars, 3.5 billion years ago. And none of that water is liquid today because Mars' atmosphere is so thin, it's only about 100th the density of our atmosphere. It's too thin for liquid water to exist on the surface. So it's either frozen or it's a gas, but no liquid water in between. Now, it's frozen at the polar caps. There's caps at both north and south poles of Mars, and these are water and dry ice, frozen carbon dioxide. This is a close-up of one of what turns out to be a set of layers, almost like tree rings, in polar deposits around those poles. So apparently, over time, Mars has gone through climatic cycles that make it warmer and then drier and warmer and drier or windier, and these layers get formed. We do think that there is some liquid water on Mars, though not on the surface. This is fairly recent stuff of a patch that was penetrated with radar, that penetrated below the surface, and found, this is kind of a side view, this is about a mile below the surface. There appears to be a set of buried lakes near the south pole of Mars. So this is what Mars looks like if you could color code it according to altitude. And I want you to notice that the northern half is blue, meaning it's low level, and it's very smooth, kind of like what you would get if you drained all the water out of Washington, the swamp of Washington. Oh, wait, out of the ocean. Out of the ocean, the seafloor would be fairly smooth and low level. And the blue is only indicative, but there are people who think that at some point in the past, much of this northern hemisphere of Mars was inundated with an ocean. And this is, again, this is showing altimetry. It's not actually showing water there. There's no water there now. In fact, you can see the craters in that area. But it is tempting to think that maybe there was this large body of liquid water at one point on Mars. Today, the water has gone elsewhere. It's not in the polar cap. There's way more evidence, there's evidence for lots more water on the surface than is now contained in the polar cap. So where did all the water go? It turns out it's frozen and underground. The blue areas here, it's a different color scheme. The blue areas are where we think ice is buried on Mars. Obviously closer to the polar caps. There's some large areas here, and maybe not very far from the surface. So we've sent landers to try to check this out and maybe to test. Viking lander, this is now more than 40 years ago, actually tested for biology, looked for life on Mars 40 years ago. And it had 3 experiments to do that. 2 of them said, no, nothing here. One of them gave some very controversial results that are still being debated by scientists. But as far as we know, there is no life on the surface of Mars. Fast forward to 2004, the Opportunity lander and rover. As soon as it touched down, it saw these little things in a little hollow, which came to be known as blueberries. They're really not blueberries, but they have a bluish color and they're about the right size. And they are largely made of hematite. And hematite is an iron oxide, not unlike rust. You've all maybe seen hematite jewelry, that has to form in water, in the presence of water. And so this told the researchers that this part of Mars had to have had liquid water on it at some point. Even today, we see in I should have had a scale bar here. These are little gullies that are racing down the walls of a crater, and they look very much like they were carved by water. So maybe the water is seeping out from the top of the crater rim and snaking down, or maybe it's something else. It could be rock slides. It could be a number of things, but it sure is making us imagine that there could be water, if not liquid, but at least very close to the surface. Here's another recent result. This is the top of a cliff. There's the bottom of the cliff. And in the cliff face, it's color-coded to show the evidence that they've got. It's not actually this beautiful azure blue. But this is showing us that there are deposits of ice within just a few hundred meters of the surface of Mars. And that's very promising, because it means that if we went to Mars, if Matt Damon really went there as the Martian, right, he might not have to look very hard to get water. So we sent a spacecraft to the polar regions of Mars, one of the polar regions, in 2015 with the express purpose of trying to find ice. And this is a Phoenix lander. It used rockets to set down, and you can see it had this sort of claw thing. There was a camera on the end, so it reached around the side to take a look to see what was underneath, and the rockets had blasted clear a huge slab of ice, just a few inches below the surface. This was incredible. This is exactly what they came for. It had the little trenching tool. It found ice just inches below the surface. How fantastic is that? So we know that the ice is there. We know it's there. And so we've sent this ever larger assembly of rovers. This is the current one, Curiosity, which is about the size of a golf cart. And it landed inside this crater called Gale. Gale crater, named after an Australian amateur astronomer. Just want you to know. Inside the crater, which is known to have water-formed features, that water must have pooled up in here sometime, is this central mound. Again, this is color-coded for altitude. It's this big mountain in the middle of the crater. And the mountain has layers in it, just like the Grand Canyon. And here's your basic geology for the day, right? The layers at the bottom of the Grand Canyon were put down first, and the ones on top are more recent. Same here inside Gale crater. We know that Mars must have been warmer, wetter, had a thicker atmosphere, say, 3.5 billion years ago. It was a pretty nice place to visit, right? Matt Damon could have easily grown his potatoes. But now, today, it's very cold, it's very desiccated, all the ice is sequestered away, the chemistry of the soil is much harsher, much more oxidizing. So what happened between here and here? That's Curiosity's job. It has been for the last several years climbing up these slopes, testing along the way. So what happened to Mars? Why did it change from being such a nice place to a very not nice place? We think that the answer lies in its magnetic field or lack thereof. I suspect some of you know that Earth has a magnetic field. And if you paid attention in school, you might have even remembered that that magnetic field is created by what's called a dynamo. There is liquid iron at the center of our planet in the core that is churning. Liquid iron is a conductor. If you churn a conducting fluid, you create or can create a magnetic field. And it's that churning core that gives us the magnetic field. Remember your little grade school experiment, the bar magnet with the piece of paper and the iron filings, right? Those magnetic field lines extend far out into space beyond the Earth's surface. And that's a good thing, because that magnetic field protects us. It creates a bubble around us, a magnetic bubble that protects us from blast waves from the sun or cosmic rays or other things that would be not so good for life. On Mars, there was a magnetic field at one time. We can see evidence for alternating bands of magnetism in its surface, but it has no magnetic field today. Its core apparently solidified and no more churning, therefore no more dynamo, therefore no magnetic field. When that happened, suddenly the planet was exposed to all that radiation, And in particular, the solar wind, the expanding atmosphere of the sun that races outward through the solar system, stripped away the top layers of its atmosphere and kept stripping it away and kept stripping it away irreplaceably. And so today, Mars has a very thin atmosphere because it has lost most of what it once had. That's too bad. These are showing you some of the ways this solar wind stripping, if once an atom gets ionized, it can be attached to a magnetic field line from the sun. There are a lot of ways. So Mars probably became very inhospitable a long time ago. And yet, within the last few years, we have seen hints that something might be stirring. This is a set of maps from Earth, color-coded to show concentrations of methane gas, which is an organic compound, very simple one, and in certain regions of Mars. And in fact, Curiosity itself has also detected methane from the surface of Mars. We see, this is Curiosity's data, it kind of, this is CH4, that's methane, parts per billion, not a lot of it, not a lot, but some. Any is better than nothing, that kind of rises and falls with the seasons on Mars. Now, there are a couple of ways to do this, to get this methane. You can do it inorganically by chemical reactions within rocks. Not easy to do. On Earth, the easiest way to make methane is to eat a bad bean burrito and wait for the consequences, right? Flatulent livestock or decaying matter create methane in our atmosphere. Now, methane is very reactive with oxygen. If you injected methane, say, a million years ago, one really big, really bad bean burrito, eaten by a dinosaur, say, none of that methane would exist anymore. It would all be converted by the oxygen. So the fact that we still have methane in our atmosphere, and we do, means that the reactions that are producing it are still going on. We are still eating bean burritos, all right, just to take that one more step. On Mars, the fact that there is methane in its atmosphere means that something is creating the methane and releasing it now. Could it be life? We don't know. We just don't know. So the exploration continues. We now, at this moment, there are 7 spacecraft in orbit around Mars and 2 roving around on its surface. So we're going to add to that in just a couple of years. There's going to be two rovers. One is the US, one's from the European Space Agency, and a lander, all of which are going to be testing in one form or another for biologic activity. Now, we don't necessarily need to go to Mars to get a sample to determine. Sometimes the samples come to us. Remember the blast, the panspermia thing, where we blast rocks off the surface of Mars? That does happen. And they do land on the Earth. We know of about 100 meteorites that actually came from Mars. And so this is one of them. This is a 4 billion-year-old Martian meteorite collected in Antarctica. And it is igneous, which is unusual in and of itself. That means it was formed out of, lava that solidified. And inside are some really interesting things scientists found when they cracked it open. There are these interesting carbonate nodules, little spheres, that have this funny rimmed, the color change shows that the chemistry is changing in the carbonate. That's very difficult to do in just a cooling lava situation, inorganically. It does happen organically. It does happen with biology. There are examples of this rimmed carbonate in the biologic world. There are also these things they found which look a little bit like fossilized, very tiny bacteria called nanobes. They exist on the Earth. They exist in some really weird places on the Earth. Could they have existed on Mars? Well, it turns out that both this and this were probably, in hindsight, were probably artifacts and could be explained away by some process. But at the time, in 1996, when they announced this result, it was a big, big deal. This is the press conference at NASA headquarters. And in fact, Bill Clinton was president at that time. He even commented, Clinton did, about this finding. And well, maybe we found life on Mars. We'll have to wait and see. The evidence has kind of moved away from that particular meteorite containing life. There is still one type of evidence called kind of special crystalline magnetite that could still be hinting that there could have been life. You have to be very careful, couch it in careful terms. You know, slight possibility, it may be, you know, there's a chance there could life on Mars. So this is kind of the way the press reacted when that was announced. I was not one of those people, right? I was much more, but we finally do have confirmed evidence that there is life on Mars. Bill Dana was right. He must have been on a Saturday night. Okay, enough of Mars. Let's move outward a little bit and move along, because I still have a lot of material to cover. This is the first time I've given this talk. So if you were looking for it to end exactly at 8 o'clock, I invite you to stick around, because it might go a little longer than that. Jupiter has 4 large moons, each of which is as large as our moon or bigger. And 2 of them are shown here. This is Io and this is Europa. Europa is a very interesting place. We've seen it up close. It's got a watery shell over a rocky core. The shell is frozen as ice. It's very, very cold. But look how smooth it is. It's like a cracked, hard-boiled egg. Smooth, very smooth. You don't see any craters. There's one maybe there, right? So why is that? Well, we now realize that Europa, that shell on the outside, right? It's hiding the chewy chocolate center that is a global ocean underneath that might in some places be only a few miles thick. We're not really sure. Different models give different numbers. But that ocean is liquid and maybe even warm. So think back to those Black Sea smokers, right? If it's a briny ocean, and if the chemistry is right, and if there's energy being supplied, who knows? So NASA's going to send a spacecraft to try to check this out a little bit more. It's been approved. It's called the Europa Clipper. I will bet you $5 that they'll rename it something between now and then. This is just sort of a working name. It's going to launch in 4 years, arrive in less than a decade, and these long antennas are radar. So the same kind of radar that penetrated through the surface of Mars to find lakes underneath will be able to tell us how thick the ice crust is and when the ocean begins, among other things. Let's move out to Saturn. And in particular, one tiny moon, not tiny, but not the tiniest, but smallish compared to our moon, is called Enceladus. It's only 300 miles across, give or take. It's cratered in some places. This is telling us that the surface is pretty old. But here, this is, again, very smooth, right? Well, smooth is relative. It kind of looks like my skin, kind of smooth, wrinkly in places. But these things near the pole, which are slightly discolored, have come to be called tiger stripes. And we have seen gigantic geysers of water erupting from those stripes near the South Pole. This is from far away. You can see them jetting out into space. This is a little animation showing that they're continuous. They're just spewing stuff. So it's not just icy. There has to be water under there. This is one more close-up. It turns out that when you fly over the South Pole, this is just the South Pole, and you take a map of its temperature, it's warm, right? The heating is coming from somewhere underneath. And it turns out that Io is volcanic too. It turns out that Enceladus is in a kind of locked relationship with a big moon called Dione, or Dione. And Dione has, it's much bigger, and it's kind of jerking Enceladus around, and it's causing tides within Enceladus in gigawatts of power. And so this is kind of a cross-section of what scientists think is happening. Inside, deep inside Enceladus, down here near the core, it's getting all this heat. The heat is creating these plumes of, like smokers, that emit hydrogen and methane, maybe methane gas in this water, briny ocean, which is getting forced up through the fractions and gets blown off into space. So, very interesting. Enceladus could be the sleeper here in terms of being able to have the conditions that are conducive for life. Now, just because it's conducive for life doesn't mean there's life there, right? As Carl Sagan once famously said, extraordinary claims require extraordinary evidence. And so we'll just have to wait and see. I'm going to move out. I've got one more to show you. Saturn has a huge moon called Titan, which is actually bigger than the planet Mercury. And it's a unique moon in the solar system because it's got a very dense atmosphere, about 1.5 times the density of our atmosphere, and it's mostly nitrogen, as our atmosphere is, but there's no oxygen. It's a complete, ours is an oxidizing atmosphere, Titan has a reducing atmosphere. It's all hydrocarbons. There's methane and ethane and all kinds of stuff, and also the surface is super cold. What we see, what would be rock here on Earth is very solidly frozen water ice on Titan. And what would be water here on Earth is liquid ethane and liquid methane. We'll see. You can see that there's this kind of hydrocarbon haze that covers the whole surface. It's smog on steroids. This is all hydrocarbon haze around. It's that color. And so we can see through the haze using infrared techniques. And this is kind of an infrared map of the surface of Titan. It's got very interesting geology. We even sent a lander to Titan in 2005, we being the European Space Agency. This is on its way down. It's floating on a parachute. It took panoramas, just like out the window of a plane. There's kind of a shoreline going on here. There are things that look like rivers. And when it landed, this is a view from the surface of Titan, a remarkable photo. And these rocks are actually chunks of ice. And when it landed, it kind of went squish. The surface was moist with liquid ethane that was kind of making it damp underfoot. Do we think that those are conditions that are suitable for life? Yeah, probably not. Probably not. So, okay. So let's go out farther. As we look out into the universe, we see that there are places like Orion, which to our eye looks very pretty, but if you could see it in infrared, you could see it's permeated with clouds of gas and dust. This is the Orion Nebula, and deep inside here, these 4 stars right here are illuminating the inside just like a light bulb illuminates a table lampshade. And inside we see hundreds of planets, hundreds of solar systems forming right now inside the Orion Nebula. It's a very easy thing to do. So the question is, how can we tell where those planets are? There's 5 ways to do it. I'm going to race through this in the interest of time because I have a whole talk on how to find planets, and this is not the important part of what I get. We can find them maybe close to stars. Here's a star that we've masked out, we astronomers, and this is a planet nearby. We can look for them wobbling in the sky, like if I were to take a 5-year-old and play Ring Around the Rosie, right? We all know what Ring Around the Rosie is, I trust. You might not be able to see the 5-year-old, but you can see me kind of wobbling around, right? That would tell you that I'm probably playing with a 5-year-old. And this is how our sun would appear to wobble as seen from 33 light years away. So that's caused by Jupiter. We can look for a kind of lensing phenomenon that I'm not going to get into, and we can look for shifts in the spectrum, which I'm not going to get into. You just have to take this on face value, because I really want to get to this one, which is for dips in the star's light. This is not a planet outside our solar system. This is the planet Venus crossing the face of the sun. It did it 2 times in 8 years apart, not that long ago. These are called transits of Venus. I hope you got to see it then, because you're not going to get to see the next one. It's going to be a long time before the next transit. But this you can appreciate that as Venus, even if you didn't know it was there, as Venus crosses the sun, it's going to block some of the sun's light. Maybe a tiny bit, a part of a fraction of a percent, but the sun's light reaching us is going to drop. And this is a technique, this transit technique allows us to look at other stars far away. We're not seeing them as balls, we're just seeing them as points of light, but we're measuring carefully how much light they are putting out. And when that light dips in a way like that, it's a very powerful technique for showing us not only that a planet is crossing it, but depending on whether the dip is deep or short or whatever, we can tell these kinds of situations. We can actually get a pretty good handle on what kind of planet, how big it is, how close it is crossing in front of that star. A typical dip looks like this. This involves a drop of about 1%. This is easy to do with modern technology. So NASA sent a spacecraft called Kepler into orbit with the express purpose of staring at a patch of sky, this patch of sky, which is over our heads once the sun goes down. When you go outside, look up, maybe it's cloudy, but that patch of sky is right overhead. It's near the border with Cygnus and Lyra. And here's the area that it searched, and it just stared there for years at this same patch of sky at 145,000 stars. That's how many stars it could detect, to see if any of them had dips. And guess what? Lots of them had dips. So all of these are 4,000 planets or candidates that Kepler discovered. And here's what I want you to know. This is a plot of the orbital period in days. What's the orbital period of the Earth around the sun? How long does it take us to go around the sun? 365 days. So Earth would be right about here. Anything shorter means it's a lot closer. And then this is the size of that planet up to Jupiter's size. So you can see that, yes, there are a bunch of planets that are Earth-sized, but boy, they're awfully close. And when these planets are this close to the sun, right, they go around in days. They're superheated. They're so close. They're 1,000 degrees or higher. In fact, uncharacteristically, a lot of the planets that are very close to their stars are the size of Jupiter. We call them hot Jupiters. We don't really know why. Haven't quite figured that one out, but there are a lot of them. The point of Kepler proved that virtually every star that it looked at has at least that it could tell. Remember, it's using the transit technique. So that means if a planet is inclined like this, right, around its star, we won't see it crossing in front. We're only seeing the planets that are statistically right, like their orbits are edge on to us. So statistically, we're not seeing a planet around every star, but there are so many that we're finding, it's very likely that most stars have planets. I'll repeat that. It's very likely that most stars have planets. And many stars have multiple planets, such that we now think that there are more planets than stars in our Milky Way. More planets than stars in our Milky Way. We have roughly 100 billion stars, round numbers, right? And we're seeing from Kepler's statistics that roughly 1 in 4 planets that are discovered are in an area that is kind of suitable, not too hot, not too cold, right, in sort of a temperate region. So that's 100 billion, a quarter of that is 250 million planets. Am I doing the math right? No, I'm not. 25 billion planets out there that might be kind of in the right spot. This is a fun little thing I'll show. So here's our solar system for scale. And there we go. So these are just some of the planet systems that Kepler found, right? Remember, it's found 4,000 planets. And these are just some of them, showing you the variety. Some of these systems have 5 or 6 planets around them. Sometimes they have one big one that's far away and two or three close ones. It's a menagerie. As many different planets as you can imagine, Kepler has found. The key turns out to be, it has to be that planet to even have hope of being life, conducive to life, has to be close enough to the star to have liquid water, but not so close that it all boils away. We call that the habitable zone. It's kind of like a Goldilocks thing, not too hot, not too cold, just right. This is a notion of what a habitable zone would be like. So these are the characteristics of a habitable zone. You want an orbital environment where it's, the orbit is stable around the star, not too many things hitting it. That would be good. We want the planet to be large enough to be able to retain an atmosphere. That's important. If it's too small, all the gas goes away. That wouldn't be good. We want to be able to get rid of the carbon dioxide. Magnetic field would be nice, right? So finally, water and volatiles to make the chemistry right for being conducive to life. So now I've taken those 4,000 candidates. I'm only showing you the ones that have planets that are roughly the size of the Earth, right, in the habitable zone. And now we're not talking about 4,000. We're talking about a couple of dozen planets that are of the right nature. Now, stars, not all stars are the same brightness. Our star, our sun, is technically a dwarf star. So you can imagine if it were smaller, it wouldn't be as hot and it wouldn't be as bright. So in order for Earth to be like Earth is, we would have to be closer to that star than we are now. Conversely, if the star were much brighter, much hotter, we would have to be farther away. So you have to gauge what the habitable zone is depending on the star. So Kepler was looking at 145,000 stars that were any distance conceivable away. Some were very distant, some were close, right? It's hard to study a planet that's, 1,000 light years away. We can't make it out. We only know it's there because it's passing in front of the star. We can't tell anything about it other than that, other than its orbit. What we really want is to find planets that are close to the Earth, in star systems that are not that far away. And so a new experiment was launched just a couple of years ago, early 2018, led by a team from MIT, by the way, called TESS. And its job is to take these huge pictures, 24 degrees on the side. So here's Orion for scale. It's basically going to take pictures, instead of just one spot, it's going to take pictures of the entire celestial sphere, as we call it, with an eye toward studying most carefully stars that are near to us, not that far away. Because then if we find a planet, we have some chance of seeing the planet separate from the star, maybe not today, but later on, and learn something about it. It's just, the results are incomplete now, but the hope is that it will find roughly 70 Earths, that is, Earth-sized planets in habitable zones that would be the sort of high priority targets for future studies. And future studies could come in a number of ways. The James Webb Space Telescope, which is the successor to the Hubble Space Telescope, is now just, it keeps getting pushed back, but it's now a couple of years away. It's a much, much bigger telescope. This is its mirror. And it's going to be looking only in the infrared, right? You've seen pictures of maybe infrared cameras. Police use them sometimes from helicopters to find someone who's hiding in the forest. They can be under a tree, but you can still see them by the heat they give off, right? Same with planets. We might not be able to see the planet itself, but we can tell the heat that's coming off of the planet and tell something diagnostic about it. It also turns out that from a spectroscopic point of view, most of the interesting chemical fingerprints are from spectral information that we get in the infrared as opposed to visible light. There's also this giant telescope called the 30-meter telescope, which may or may not be built on Mauna Kea in Hawaii. This is the one that's very controversial and being constructed right now. But it too has a major goal of searching for extrasolar planets. This is a sense of what I was telling you. Here is a spectrum. This is basically, this is visible light here down at this end, and then this is infrared. A spectrum of the Earth's atmosphere would tell us that we have ozone, oxygen, water, and carbon dioxide. A spectrum of Mars, the red line would say carbon dioxide and not much else. Ditto with Venus. Both of their atmospheres are predominantly, if not exclusively, carbon dioxide. Earth has a much richer spectrum because it's got a much more interesting atmosphere. And then finally, one idea is to use a technique to block out the star with a special mask. That's a spacecraft in orbit, separated by a long distance, and cover the star so that we can pick out the planets that might be on either side of it. That's a technology that's also being developed by MIT and JPL and other places. Maybe within the next 10 years, we might have one of these called star shades. So the goal here, I am getting near the end. The goal is to find as many Earths. We're looking for Earths. We're looking for planets that are rocky and roughly the same size of ours. It won't do us any good to be a Jupiter because we don't want a big shell of hydrogen around us and no solid surface. We want something that is like the Earth in size, has enough mass to hold onto an atmosphere, is around a stable star that's just not too hot, not too cold. And by the way, has water. Okay? That's a pretty long checklist, and that's the goal. And guess what? We're starting to find, this is a hypothetical cartoon, right? But this is real. These are planets that we have already found that, they're different. Some are pretty close. This is Proxima Centauri. This is the closest star system to Earth. just 4 light years away versus 1,200 light years away. But they're out there. They're out there. We're starting to find them. So speaking of Proxima Centauri, we don't have to just sit by. Maybe we, hypothetically could go visit them. 4 light years, it's 25 trillion miles. It's a lot of miles, right? It's a lot of miles. So there's a notion led by the late Stephen Hawking and others called the breakthrough starshot is what it's called. And the notion is they build a little tiny spacecraft this big. And then they put it on a sail that's roughly half the size of this room, just a gossamer wing. And then they fire a laser from Earth at it and push it with the laser to 2/10 of the speed of light. And at that speed, it will reach the Proxima Centauri system in about 20 years. Now we're starting to be, a reasonable notion here of something we could do within our lifetimes. Then it would study that planet or that system, and it would use radio to send us stuff back, but still it's 4 light years away, so it would take a while. It's an idea. We're not there yet. But who cares? They're already coming to visit us. Right? So the notion is, what is the chance that there really is intelligent life elsewhere? Intelligent life. Now, I used to teach high school astronomy, and I would say to kids, how many of you ever saw that really bad Kevin Costner film, Waterworld? Grown, right? Okay, so imagine that the Earth had more water than it does, such that there would be very little land, lots of ocean, but everything else was unchanged. In that case, as evolution proceeded, what would be the dominant life form on the Earth right now? Marine life. And in particular, the smartest are dolphins and whales. We would agree that they're intelligent, they have social structure, they have communication, right? They are intelligent creatures. They're never going to build a rocket. They're never going to build a radio telescope. So we have to be careful how we define intelligent life. This guy, Frank Drake, who's still alive, in 1960, he used this telescope down in West Virginia to study for the first time listening for radio communication from another planet around a couple of nearby stars. He didn't hear anything, but it didn't stop him. He is the founder of the Search for Extraterrestrial Intelligence, or SETI. And so he's come up with this a little bit out of order. This equation is called the Drake equation, and it tries to estimate how many technologically advanced civilizations might be out there trying to communicate with us. And so each of these has oh, that's not breaking right. Sorry, this is going to be messy. So the average rate of star formation in our galaxy times the fraction of those stars that have planets times the average number of those planets that could support life times the number of those planets that do develop life times the number that actually evolve into intelligent civilizations, dolphins, whatever, and then the fraction of those that develop technology able to send out radio signals, and it's a diminishing return. It turns out that we have finally, the lifetime that those civilizations have where they're able to do that. We've had this capability since early in the 19th century to actually have radio, right? We're now early in the 21st century, so we've been at it for about 100 years. If we blow ourselves up to smithereens or global warming sweeps us away or whatever, then our lifetime would have only been 100 years, a blink of an eye. So the name of the game is to last a long time here. So we can make some estimates about the first 3 of these. The average rate of star formation in our galaxy is about 1 mass of the sun per year. That our galaxy, the Milky Way, makes about 1 sun per year on average. And we now know, thanks to Kepler, that most of the stars have planets. And we even know that we're even starting to guess that roughly a quarter of them might be a situation that is conducive to life. All this other stuff, it's just guesswork at this point. But that hasn't stopped people from listening. And so there are all these teams that are using radio and laser technology to listen for the possibility that there is somebody trying to communicate with us, rather than actually visit us, right? E.T. notwithstanding, it's a lot easier to just shout with the radio, hello, we're here, than to actually go visit. And nothing has been found yet. This is one particularly ambitious one out in California, funded by the late Paul Allen, run by a place called the SETI Institute. And we have even tried to send communication outward on the Pioneer spacecraft and the Voyager spacecraft. We send out like little vacation postcards saying, hey, we're out here on Earth, come visit us. Stephen Hawking doesn't like that idea because if aliens visit us, the outcome would be not so well. But other people think it's a good idea. And this is a message that was beamed to M13, which is a very rich star cluster. But he said that we should send Bach, but that would be boasting. All right. So I'm going to end. I was looking for a suitable. This is the end. There have been a great many science fiction movies that talked about us visiting them and them visiting us and so forth. Interstellar, the list goes on and on. In my mind, the very best movie on this particular topic is Contact, which was in 1997. It was written by Carl Sagan and his wife Andrewian. It featured Jodie Foster as a young scientist, a radio astronomer who used giant radio telescopes to try to listen for intelligent life elsewhere. Guess what? She was modeled after a real person, Jill Tarter. They're on the set there at the Arecibo radio telescope in Puerto Rico. So Jodie Foster was portraying a real female scientist who really did this. And Jodie has said that she worked really hard to try to capture what being a scientist, a female scientist, but doing the science right in the movie, what it really would be like to actually discover a radio message from outer space from another intelligent being. And I would like to close with just a 4-minute clip that I think kind of says it all.
Right ascension, 18 hours, 36 minutes, 56.2 seconds. Hey, is anybody awake in there? I'm moving the array. Confirm.
Boss has a bogey.
Right ascension, 18 hours, 36 minutes, 56.2 seconds. Declination.
We're on it.
Plus 36 hours, 47 minutes, and 1 second. Strong possible pulse chain on subarray formed. I'm moving the rest of them now, and I need you to confirm the coordinates.
Check the status of the array. She's doing all the dishes. All systems nominal. Hello. I need a full systems check.
Coordinates confirmed. Willie's checking the system now.
Stay on top of the systems diagnostics. Check the reference pointing offsets. And
This is a real array of radio telescopes in New Mexico. This was not some computer-generated thing.
Copy that. Willie, yeah, go, Ellie.
Because I can hear it on the headphones. So we gotta be sure about this.
Give me another array status. Her 4 are online. The rest
rest are tracking in.
Your 4 are online, the rest are tracking in.
But there's a bad drive on 16.
Your 4 are online, the rest are tracking in, but there's a bad drive on 16. Copy that? What do you want me to do about the source queue?
Look, forget about it and hold the queue. Go get ready to set the target frequency to manual the second we're aligned. Did you copy? I want you to go off axis on 27 the second we're there. And leave the LO frequency where it is. Stay on it, fish, don't let it get away. If you lose it, just scan the band. Run every frequency you can think of. How you doing? Talk to me, guys.
Partially polarized set of moving pulses, amplitude modulated.
We're locked. Systems check out, signal across the board. What's the frequency?
4.4623 gigahertz. Hydrogen times pi. Told you.
Strong sucker, too.
I got it. I'm patched in.
All right, let me hear it. Listen to that.
Well, maybe someday, that's a little dramatized, but that dialogue makes a radio astronomer weep. It's so good. And so we don't know where or when we're going to discover life elsewhere. We're certainly trying on multiple fronts, as I hope you've seen tonight. And, you know, it's not a capricious search. It's obviously very low odds of success. It's a needle in a haystack kind of thing. But imagine how our society would change if we were to confirm that there is life somewhere else of whatever kind within the next 5, 10, 15 years. It would be a very dramatic day, and you'd probably have me come back and give another talk. Thanks all very much. All right, thank you for putting up for the little bit of extra time. Questions?
Quick one. How many of those candidate planets that they've discovered so far are binary systems?
Oh, okay, so his question is how many of the candidate planets are binary star systems, right, where there are 2 stars, and I don't know the answer, but I think they're all, I had not heard of any that are binaries. So, and the reason is, unlike what you saw in Star Wars and Tatooine, it's a binary star system is generally pretty unstable for having a stable orbit for a planet around it. And so that would not be your preferred. Yes, in the back.
So could the same thing that happened to Mars's core happen to our core?
Yeah, so his question is, could the same thing that happened to the core of Mars happen to us? Yes, and it will eventually, but not for a very long time. So Mars, because it's half the size, has 1/4 of the surface area, right? But 1/8 of the volume. And so it has a higher surface to volume ratio, and so it was able to radiate away its heat faster and cool much more quickly than the Earth has. The same notion is if you took, if you had 2 cups, if you had a cup of coffee and a giant pitcher of coffee at the same temperature, which one is going to come to room temperature first? The cup is, right? Because it's able to radiate the heat. So Mars, it went dead 3 billion years ago at least. We're in good shape for now. However, I will say, one of the things that happens to the Earth's magnetic field periodically is that its polarity reverses. And we don't know what's going to happen then. It's probable that what will happen is, inside the core, we had an article on this in our magazine a while back, that it won't just go like this, it will kind of collapse, reassemble itself, and then reemerge. And we don't know how that, scrambled part, how long that will last, maybe 1,000 years. Could be very bad. We don't really know, but we know it's coming. So in a sense, there is a time coming when we're going to have no magnetic field, and we're not going to lose our atmosphere in that little bit of time, but it will definitely make us more susceptible to radiation. Plane flights at high altitude, for example, will get a lot more dicier. You'll land and you'll glow. that kind of thing. Yes?
You said that molecules were left-handed.
Yes.
Is that correct? So we could surmise that God is left-handed.
Yes. Or he was looking at the mirror at his right hand. One or the other, right? Yeah. So that that's chirality thing is a very, very important signature for life and biomolecules, bioorganic molecules. Yes.
How did they know those rocks like the one in Antarctica came from Mars?
Yes, so his question is, how did we know that the Mars rock was really from Mars? So our landers have been to Mars and sampled the atmosphere. And the atmosphere has a mixture of gases, but those gases each have characteristic isotopes. Neon, for example, and oxygen both have very characteristic isotopes in mixtures. You've probably all heard of carbon-14, right? Carbon-12 is the normal everyday form of carbon, and there's just a little tiny bit of carbon-14. So when we see things that have a concentration of carbon-14 in it, that's telling us that there is that was life-induced, biologically induced. Okay, so we know what the isotopic ratios are on Mars in the real place, and when a meteorite comes to the ground and we test the isotopic ratios of little gas bubbles and such within the meteorite and they match, then that tells us. It's also the case, I mentioned that it was an igneous rock made from molten rock, that solidified 4 billion years ago. That doesn't happen in the asteroid belt. There really aren't any places besides the terrestrial planets. So it either had to be Mars, Venus, or Mercury, and Mars is the one that it matches. Oh, yes?
Why are we always looking for life further away from us? Is Venus too hot?
Oh, great question. So why are we looking so far? How about Venus is too hot? Venus, has a cautionary tale itself. It is too hot. The surface temperature of Venus is about 900 degrees, and even the thermophiles would have a tough time with that. Venus has a very dense atmosphere that's almost entirely carbon dioxide, 90 times the pressure at its surface of the pressure on Earth, and all of it carbon dioxide. It's what we call a runaway greenhouse. And yet, the global inventory of carbon dioxide on Venus and Earth are about the same. We are lucky that we had water. We are lucky that the temperature was a little bit, what happened on Venus was the water all kind of boiled away and went to the top of the atmosphere. Venus has no magnetic field. The water got stripped away, right? Irrevocably. So the water disappeared. Therefore, Venus had no oceans into which to dissolve the carbon dioxide and have it make nice beds on the bottom. Venus also has no plate tectonism, so its carbon dioxide just stayed on the surface instead of getting dragged into the mantle. For all those reasons, the carbon dioxide remained viable to heat up the atmosphere, and that's why it's all in the atmosphere. On our planet, it's all underground. We're lucky. So it's a delicate balance. Sometimes, a few tens of millions of miles makes all the difference. This is why the habitable zone is so important. The habitable zone in our solar system isn't super narrow. It kind of goes most of the way to Venus and most of the way to Mars. So it's a fairly broad area where you could imagine Earth having ended up, and we probably would have been pretty much the way we are. And this is why we're looking around other star systems for that habitable zone. We're looking for Earths, we're not looking for Venuses. Mercury is too close and has no atmosphere. So yeah, there aren't very many places, and that's why what's really interesting are these, not the outer planets themselves, but their moons, their icy moons, we wouldn't have guessed that they had these buried oceans, but they do, and that makes them biologically potentially very interesting.
Has the habitable zone expanded or contracted as the sun ages?
Great question. This question is, has the habitable zone expanded or contracted as the sun ages? Little known fact is that the sun was not always as bright as it is now. There's something called the faint early sun. And the paradox, and it's called a paradox, is how did life arise on Earth at a time early in our history, primordial Earth, when the sun wasn't as bright, so it was colder here. Of course, we were still more molten, but this has special implications for Mars. So the question is, how was it that Mars was somehow warm enough to have all that water flowing on its surface? Because the faint early sun, if you run the numbers, Mars should never have been warm enough for that to happen. It should have always been a cold, frozen place. So as time goes on, the sun is gradually going to get more and more bright, brighter and brighter, also bigger. It's going to swell up, and it's going to swell to the size of a red giant. It's going to take out Mercury and Venus. It may or may not take out the Earth too, before it finally sheds its outer layers and becomes a white dwarf star. When it sheds that, we're talking like 4 billion years in the future, so you don't need to like change your vacation plans. One more question, and then maybe we'll call it a night.
There's projected that we're going to go to Mars in the next 20 years, 25 years.
With humans, you mean?
Man.
Yes.
Yes. How will we get water up to Mars? Are we going to shoot tankers up there?
Oh, so there's lots. So there is lots of water on Mars. It's just buried as ice. And so the question is, I mean, for example, we could land on one of the polar caps, and there'd be abundant water all around us. Well, you just run it through your sock, and it'll be fine, right? So there. Water is not the issue. We don't think water is going to be the issue on Mars. Maybe it's a trade-off, because the warmest places on Mars, where you have to heat yourself up the least, are like the equatorial regions, and there's not much water there. But the closer you go to the poles, the more abundant the ice will be at or just below the surface, we think. Well, thank you all very much for coming. It's great to be back here, and please go watch Contact. It's an awesome show, and it will kind of put you'll take everything you got tonight and put it in the context of that movie. It's a great movie to make you all think big thoughts. Have a great night, everyone.